talking about Newton's 3 laws, talk about how they affect objects in the universe. And really, Newton's laws allow us to basically predict all of the movement of objects throughout the universe. And scientists have used Newton's laws to predict how the path that the planets take around the stars and the movement of those, how a projectile flies through the air, all sorts of various physics phenomenon of moving objects can be explained by Newton's 3 laws. And so we're going to learn a little bit about those, just sort of the basics about what each of the laws means and some examples of it. These are things that you would explore further when you get to physics in high school. But first off, Newton's laws talk a lot about forces. And when we talk about a force is a push or a pull on an object. And when we talk about Newton's laws, we talk about 2 special forces, sort of, that are important on Earth and other places. And those 2 forces are gravity and friction. So tell me something about friction. What exactly is it? Nicole?
It's like when something is rubbing up against another.
Yeah. Friction is a force when 2 objects rub against each other. It's a force that opposes movement. And so different types of surfaces have different amounts of friction. When I'm walking right now, my shoes are pushing against the ground. Okay? There's a certain amount of friction there. But if I were on ice and I push against the ground, my foot would obviously slide. That's because ice has much lower friction. It's why I can't slide across this floor, but I could slide across the ice. Or if you're on a hardwood floor in your socks, you can probably slide for a little ways, but if you're on the carpet in another room, you can't. The difference between those is the amount of friction between those surfaces and your feet. So friction is a force that resists motion. Friction also, this force that resists motion, also generates what? Heat. And so, like, if you rub your hands together, you guys see the original Karate Kid?
Yeah.
Mr. Miyagi, he does this, then he fixes Daniel-san's leg or whatever. But they took that out of, like, the newer one, right?
No, I've never seen either. They did some fireball.
Yeah, it was late. They should have just kept the old one. Anyway,
I like the old school.
that's that friction generates heat. It's why it hurts when you slide on the gym floor in your leg. You get a floor burn or something like that. So friction is a force that opposes motion. There's also the force of gravity. And gravity is a force between all objects in the universe. And gravity is an attractive force. So we know that when we jump, we return back to the earth because of the force of gravity, because there's an attraction between the mass of the earth and us. But what you may not know is that attractive force is mutual. Not only are we attracted back to the earth, but the earth is attracted up to us when we jump. But when I jump, why does the whole room suddenly move up to my feet?
Well, because it's not possible.
Why?
Because gravity. No.
No?
Because the room is attracted down.
No?
Yeah, because
Hold on.
it's smaller here. The actual stays down, and that's what stays down when you stay down.
No? Jonathan?
Earth has more mass.
Because of the mass. So the mass of me is very tiny compared to the mass of the entire Earth. So when I jump, I'm attracted, the Earth is attracting me, but the force that the Earth can move is minuscule because my mass is so tiny. But the mass of the Earth is so huge, the attraction is much more, and there's much more movement, me towards the Earth, rather than Earth towards my feet. Courtney?
If like a billion people jump on the Earth, would it move?
the mass would still be tiny compared to the entire mass of the Earth, even if it was a billion people. Gotcha. And you wouldn't, it's not even, wouldn't be able to be measured, but they're still, I guess, tempted. All right, Jonathan, you have a question?
Well, the formula for force is force equals mass minus acceleration.
Yeah, we'll get there. But before we get there, we're going to talk about inertia. So the law of inertia states that an object that's at rest will stay at rest, and an object that's in motion will stay in motion. Pretty common sense. Unless, there's an important unless to this, unless it is acted upon by some outside force. So when I talked about rolling this ball, so this ball, it's going to stay here. It's at rest. It's going to stay at rest. The only way it's going to begin moving is if some outside force acts upon it. Me pushing it is an outside force that moves it. Now, technically this ball should continue rolling forever, but it doesn't. And that's because there's an unless. So when this ball is in motion, Newton's law of inertia says it should stay in motion unless acted upon by an outside force. And you guys just told me earlier, there is an outside force. It's the force of friction, or it's the force of air resistance. Okay? So that's the law of inertia. And the law of inertia can explain many different things that we observe sort of in our everyday lives. One example is that when you ever see a person yank a tablecloth off of a thing. So if I try this trick,
Oh God,
I know.
Oh, don't put your
So-
Mr. Duras, don't please. No, you're gonna break something. Sachin.
So if I have a container of water here right in front of Sachin and Olivia, and I am going to yank this tablecloth out from under it. Now, this water is at rest. So because of inertia, its tendency is to stay at rest. Now, are there going to be any outside forces acting upon it?
Yeah.
Yes, somewhat. The outside force is going to be this piece of plastic coming out from under that. Now, so let's see.
If you mess it up a left.
Got your glasses on, right?
I thought you can't water.
All right.
How'd you do that?
So could I have done this using a section of a rug instead?
Yes.
No. If I had like a carpet, a little scrap of carpet, and I pulled it, this water would go flying. So again, what's the difference? Yeah, the friction between this surface and the container of water is relatively low. This is pretty smooth, pretty slippery. Carpet would have much more friction, and so it would exert a much greater force that would probably send this water flying with it. So that's an object at rest, it stays at rest. Same thing if you know, this one's sometimes harder. If you have like a ball here, okay, so again, if the ball doesn't go flying off over here, because again, it's at rest and it tends to stay at rest. If I can get this cardboard tube out quickly enough and with less force here, now this is covered in tape that's kind of a high friction, so it moves a little bit. But again, it tends to stay at rest and sort of drop straight down rather than going with this as I knock it out from under it. Yeah, Nicole?
Is that like the same thing with a bucket of water and you go like that?
Sort of. That's called centrifugal force. I'll do that one too another day. Swing a bucket of water over your head. Yeah. But that is based on. So that's based on inertia, because as you swing that water, it tends to stay in motion and push against the side of the bucket. But that's sort of a special case that we'll talk about. Can you see my clicker? Oh, there it is. All right. So the objects that are on the tablecloth are at rest, and they will tend to stay at rest. This law of inertia also tells us why we're riding our little red gym scooter down the floor, and let's say Tristan stuck his foot out and stopped my scooter from moving. What would happen to me?
You would fall.
Fly out the
Why?
windshield. Because of the law.
Because you're moving.
No, Ashley?
Because when your scooter stopped, you were still moving.
Yes. I was in motion. And even though my scooter stopped, I am going to continue in motion and go flying out. It's like if you're riding your skateboard down the hill and you go into the grass, you go flying because you have inertia. You're in motion. You'll tend to stay in motion. If you're in a car, riding in a car, if you don't wear your seatbelt and there's an accident, again, that's why you can be ejected from the car, and that's why it's dangerous, because you're in motion, moving quickly in that car. If the car suddenly stops, your body, because of its inertia, will continue in motion. Okay? So, have here, to be very
Wait, let me see. Whoa.
I'm thinking about getting a job at Pixar,
You need to.
based on my
This is
computer
as
graphics
good
work.
This is as good as their shorts, if not better.
So again, Mr. Motorcycle here hits the wall, he continues in motion as inertia. No, I know it looks realistic, but this is not a real video. It's animated.
Are you sure?
Yeah.
Why is he spinning over
Uh-oh.
Wow, way to build a
That was so
fire.
epic.
How
What?
long did it take you to make these?
Which guy? He's wearing a seatbelt. So when you wear your seatbelt, basically you are attaching yourself to the inertia of the vehicle you're in. So when the vehicle slows down or stops suddenly, you stop with it. But it can also explain why. So if you're in the car with your mom and you're late to school and she's in a hurry and she's at the stoplight and she hits the gas, what happens to you? You go forward? Think about it. No. When your mom hits the gas, you get pushed back. You get pushed back against your seat. Again, what's happening is this is you. This is your seat. So when she hits the accelerator, you're at rest when you're at the stoplight. The car moves forward, pushing the back of the seat against you, and you tend to stay at rest. At the same time, you're moving very quickly. Your mom's tailgating the person in front of you, has to slam on the brakes. What do? That's when you go forward, because you're in motion. The car stops, but you continue in motion, and you go forward towards the dashboard. So again, this is because of the law of inertia. Joey?
The one on the bottom.
They all
So Mr. Ross is the one in the middle and the top piece. Whoa.
All right, yes, I have a question about inertia.
Is that why that one ride at the Broomfield Fair where you're not strapped in?
Yeah, that's also centrifugal force, like the water in the bucket. Oh, let me say one more thing here. So you guys have asked about this before. So this is a pendulum. So this pendulum is just a weight attached to a rope. And so it swings. Now, this pendulum, if it were in a complete vacuum, would swing for how long? Forever. But it doesn't. Okay, obviously, the pendulum it slows down each time it doesn't quite get back to its original height because of what forces here? So what are the main forces? Well, gravity is not slowing it down, and that's what's moving it. Yeah, the main force is air resistance. So as this weight swings through the air, it's running into billions of air molecules, molecules of oxygen and nitrogen, and they take their toll. They slow it down as it's moving through the air. Okay? And so that's the main force that resists it. There is a tiny amount of friction. You know, this is attached to a paper clip up there. There's not much friction between that paper clip and what it's attached to, but there is a small amount of friction. And so if this were in a place with no friction and no air resistance, then this should swing forever. But obviously on Earth, it doesn't, because those aren't the conditions. So now if I do this, if I hold it at my chin and let go, okay, should I be worried?
No.
No. I just have to trust in the laws of physics.
Come on. Oh, he needs your neck back.
Did I?
Yeah.
All right.
You don't trust. Go from your nose.
No,
No,
laws of physics, and I know air resistance is going to slow it down. It's not. Now, what's up, Grant? Is this a good idea?
No.
No, that is a bad idea, because again, I'm not just allowing gravity, I'm giving it some forward force.
Do it and then close
It
your
will
eyes.
return. It will return back up to its normal height. No,
What's that board there for?
it's an official pendulum attachment board.
Oh my
What
god.
pendulum do you have?
All right, let's talk about Newton's second law. So Newton's second law is a law that has to do with the forces we apply to an object and how they can make the object move. So in Newton's second law, we say the greater the mass of the object, the greater amount of force to accelerate it. Okay? So if I'm standing on this scooter and somebody pushed me, I would accelerate at a certain rate. However, for Mr. Arcuri standing on the scooter, someone would have to apply a much greater force to accelerate him at the same rate. And so we have a formula we use. And the formula is the force applied is equal to the mass of the object times its acceleration. And this is one of those mathematical formulae that can be used to find any of the misses. So if you know the force that's being applied and you know the mass of the object, you can calculate how quickly it will accelerate. If you know how quickly the mass of the object accelerates, you can figure out the force that was applied. And so you could find any two out of the three if you have the necessary information. So this is sort of common sense. It takes a lot more force to move a cart filled with something than it would to take an empty cart. Again, that's because the mass is less. It's going to take a smaller force to accelerate it.
Handwriting's extra bad today.
Comment, Mr. Dulas. The stuff inside of the car.
You already made a Star Wars reference, don't investigate.
Makes sense.
So, Mr. Dulas, the stuff inside of the cart is like the stuff from when we sports. You know when you play tennis and then like you mess up, it shows like clouds. And
Oh yeah.
Oh, yeah?
It kind of looks like that.
All right, cool.
Good.
So yeah, there's
Visualization, Mr. Dulas.
all right, now, so if we look at a couple of basic examples of how we use Newton's second law.
Yes,
So we
please.
have Mike here. Mike's car is out of gas, so he has to push it to the gas station. He's trying to accelerate it to at an acceleration of 0.05 meters per second squared. So we can use Newton's law to determine how much force Mike has to apply to the car. So we, again, set up our formula. We substituted our numbers. 1,000 kilograms is the mass of the car. It's going to accelerate at 0.05 meters per second squared. And so what force does Mike apply to this car? Cool?
50 kilograms per meters per second.
All right, good. So 50 kilograms times meters per second squared. Now the good news is we have a shortened unit
Oh, good.
that we use. We generally don't use, such unwieldy units. And this unit is named after a famous person.
Not Mr. Dulas.
Oh,
Yes, it is newtons. 50 newtons of force had to be applied. Nicole?
Is that just always kg?
Yes. A newton is a kilogram times a meter per second squared. That's it. Because remember, acceleration is meters per second, meters per second squared.
what is excess?
Wait, is that Newton?
The
guys?
times.
Oh.
All right, so now we have Bob. Bob,
Mine's Bob.
well, Bob is, sounds like Bob's a hippie. He's driving his, his Volkswagen bus here. He's going to, a Grateful Dead concert. But anyway, he ran out of gas as well, and his van is much larger, but he also wants to accelerate at the same rate. So you don't even really probably need to do the calculation. what force would Bob have to apply? Nicholas?
500.
No? Emma?
100 newtons?
Yeah. Why did you figure out so quickly?
Because because the first one was 1,000 and then the second one was
Yeah, we've doubled the mass, and therefore he would have to use double the force.
Okay,
All right, so that is our second law of motion. Force equals mass times acceleration. The greater force we apply, the more acceleration that the object will experience.
Why would you punch someone?
You shouldn't, but let's just use that as an example.
Whoa!
Newton's third law. So Newton's third law states that for every action, there is an equal and opposite reaction. Okay, so it means that every time a force is applied to one object, there's also an opposite force that's applied that's equal. So, although I don't condone violence, if a person were to punch somebody else, maybe while boxing, let's say,
Yeah, MMA.
Where's his glove?
I'm bare-knuckled boxing, and
That's just
when a
funny.
person, if you were to punch an imaginary boxing dummy, this is, not a real person, then as you exert a force on that object, it also exerting a force back that's equal in force but opposite in direction. Okay? And therefore, if you punch something, it hurts your hand because you apply force to the object applies an equal force in the opposite direction. Okay? So if I push on this counter with a certain force, it pushes back on me, okay, with a certain force, and that's what causes me to move backwards. Now, why, if I'm just standing here and I push against it, do I not move? Right, because my shoes have a lot of friction. When I'm on my little rolling cart here, there's much less friction, and so that force actually can move me. And the greater force I apply to the desk, the greater force it applies back, and I move faster. This is how jet propulsion works, like a rocket or a jet engine works, or a balloon that you blow up and let go. As a gas comes out of that balloon or the rocket at a high speed, it exerts a force in the opposite direction. And that's what propels the rocket through the air. Ejecting these gases out at a very high rate of speed moves the rocket forward. That's what happens. If you were to jump from a canoe onto a dock, okay, again, you can get to the dock, but what happens to the canoe? It moves backwards, right? You push it away because you're exerting a force to jump onto the dock, but there's an opposite force pushing on the canoe, which sends it moving away. So my animation skills have improved.
You're never going to get that canoe back without getting in the water.
So, all right.
Judas, I don't recommend this.
What?
Like jumping that far, that looks like a long
You have to be very skilled.
It's like a fucking jump.
All right, a couple other things. So let's say Bob, who is trying to get his van back to the gas station, has this brilliant idea. He says, well, I go a lot faster when I'm rollerblading. I might as well put on my rollerblades and I'm going to be able to push this van much easier. So, is rollerblading still a thing?
Yes.
How about roller skating? All right, so anyway, as Bob pushes against the van with his rollerblades on, is it going to be effective? No, he has much less friction on his, so what's going to happen to him? He's going to go backwards. He's not going to be pushing the van forward. The van is going to be exerting a force on him in the opposite direction, and he's going to get pushed backwards. So when a person fires a gun, there is what's called a recoil. There's a force that pushes back. A larger caliber weapon has greater recoil, and when a person fires it, there's kickback. And the reason for that, again, is because of Newton's third law. As the bullet is ejected from that gun at a high rate of speed, there's an opposite force pushing back. And that's what causes that recoil, that kickback. Nicole?
If like if it wasn't like something that's heavy and he pushed it, would he go further and wouldn't that be like another law?
What do you mean?
Like if it was light and then
If this object were light
Yeah.
and he pushed it with his rollerblades on?
yeah, if you push
He
it
could. It would be depending on the masses and the forces and the friction. You know, it doesn't matter really how light it is. If you're wearing your rollerblades and you push, I mean, I guess you could push like a box or something, but still, there's so little friction that you're probably going to roll backwards. Courtney?
Is that why when you like blow up a balloon and then let it go, like it flies everywhere?
Yep. That's because those get, or like, I didn't do those bottle rockets you put water in and pump up with water. They go flying because they're shooting out this water and air at a very high rate, and that pushes the bottled rocket up. Jonathan?
Why is that guy holding the gun incorrectly?
I don't know. He's not very. He didn't take his gun safety course.
Herschel.
Herschel.
Okay, so,
All right, let's listen to Herschel.
quick story.
No!
Go ahead.
Tristan.
All right, Tristan.
So I'm on my ripstick.
Right now you are?
No.
Oh, once you were on it.
I
Okay.
were.
Go ahead, continue.
I pushed myself
Uh-huh.
and then went forward.
Oh my god!
Good story. All right. Any other questions?
It was so
Push yourself and move.
Let's do this real quickly. So if we summarize Newton's 3 laws, Newton's first law is the law of inertia. Object at rest, stay at rest. Object in motion, stay in motion. What's the important unless?
Unless acted upon by the opposing force.
Unless acted upon by an outside force. We don't really use a mathematical expression for it. An example would just be an object sitting on a table. It stays there. It stays sitting on the table unless a force acts upon it. Newton's second law. Okay? The more mass an object has, the harder it is to move. And we do have a mathematical expression that helps us calculate this. F equals ma. Force equals mass times acceleration.
Sounds like some kind of soccer thing.
FEMA is a Federal Emergency Management Agency. An example takes a lot of force to push a heavy wheelbarrow versus an empty wheelbarrow. Why? The more massive an object is, the harder it is to move. Adding that one word completely changes it. All right, and law 3. A reaction is an equal but opposite reaction. You push a wall, the wall pushes back.
Has an
Equal
You need some grammar.
but opposite reaction.
I'll go get Mr.
That makes complete and total sense. Every action has an equal but opposite reaction.
Oh, I think
My
it's
wrist sticks
equal,
on it.
comma.
My ripstick's
Like,
Why? You saw an invisible comma there, Nicole?
No,
Yes,
like the
it's
way you
right
said
there.
it sounded like that.
Joe, it's not smart.
Reaction has equal, but
You have any more?
No, this is my only scooter.
Where'd you get it from?
Where can I get
Gym?
I borrowed it from the gym.
you can't get confused. Oh, you probably did.
Uh-oh, quick time HC64 decompressors needed. Tomorrow I'll watch, I got student-made stop-motion animation, Lego, about Newton's laws.
Oh, I can do stop motion.
You do? Did you do this one?
No, I wish I did. I'll be so popular.
It's really good. I don't know how he did it. I don't know.
I don't do stop motion.
It's really good. What?
Are you gonna eat that?
Yeah. Why? Yeah.
Mr. Fury's class thought there was actually a person coming into the classroom.
What do you mean?
Like they thought